All right, we're in section 10.4 where we're going to find probabilities of disjoint and overlapping events. So anytime we have um, anytime we're trying to figure out where we would have like multiple currencies or trying to find multiple probabilities. Basically, we're trying to find what is called compound events. Compound events can be uh, either like a union or an intersection of two events. Now, when we're dealing with either a disjoint or mutually exclusive event or an overlapping event, what that means is we are trying to find the or statement of the probability. Okay, anytime you're dealing with an or statement of a probability, you are looking for one item. All right, the question is that one item uh, go together with the two items that you're talking about, which is why we talk about overlapping events, or are they mutually exclusive? They have no bearing on each other at all, and that's where you get the disjointed or mutually exclusive. Um, Here are the formulas for these types of events. So if we have an overlapping event, you are saying that it's the probability of this or this happening. You are going to say, okay, if they overlap, you're going to take the probability of A plus the probability of B, but then you're subtracting the probability of A and B happening together. The reason for that is because you don't want to add things or you don't want to have certain things that are coming into play that wouldn't work out. It would make the probability incorrect. So if you had two items that were mutually exclusive or disjointed, you are just going to look at this formula here where it's just the probability of A plus the probability of B. So you have to be able to figure out first off what kind of compound event are we looking at? So this would be an example of a mutually exclusive event, all right? All we have in this set here are smiley faces and stars, and all we have in this set here is just flowers, okay? So mutually exclusive, you know, they have no ties in the probability. If you look here, this is where, if you had something like this is where, the union comes into play, and you would have to take into account not only the probability of set C plus the probability of set D, but you also take in the subtraction of the probability of A and C occurring. All right, and I'll show you examples of that in different aspects of these example problems. So what we have here, it says a standard deck of cards is chosen at random. We want to know the probability of selecting a 10 or a spade, all right? Selecting a 10 or a spade is an overlapping event because there are some uh, cards that are 10s, and there's also some cards that are spades, and there are some cards that are both 10 and spades. So we have to take in that into account. So to look at the solution, we can say, all right, we know that there are 4 10s and there are 13 spades, and there is one that is both the 10 and the spades. So we write the probability of that. So it's going to be the probability of selecting a 10 plus the probability of selecting a spade, and then subtracting it by the probability of selecting a 10 and spade. So number of spades in this, or another tens, I'm sorry, were 4, so it's 4 out of 52, plus the number of spades, which is 13 out of 52, and subtracted by what's both 10 and spade would be 1 out of 52. All right, you add all those up, you get what, 4 plus 13 plus negative 1, you get 16, so it becomes 16 out of 52. Put that into lowest terms, it's going to be equal to 4 out of 13, and it's roughly a 30.8% probability of that occurring. All right, so now we look here. They want us to find the probability of a 10 or a face card, right? This is an example of a disjointed or mutually exclusive event because there are no 10s that are face cards and there are no face cards that are 10s. So we can say that this is going to be the probability of selecting a 10 plus the probability of selecting a face card. So there are 4 10s, so it's going to be 4 out of 52, plus there are 12 face cards, so it's going to be 12 out of 52. Add those together. Again, this is 16 out of 52, which gets reduced to 4 over 13, which this is also 30.8%. Okay. Next, they want us, we're going to look at what is called a complement of an event. So anytime you have this like horizontal line over an event or something like that, they want to know what the complement is, which is basically you're trying to figure out the outcomes that are not part of the event. So the formula for using the complement of a probability. So the probability of finding things that are not part of that event is going to be equal to 1 minus the probability of A, all right? Using the complement is helpful when faced with probability problems where the number of outcomes of the event is much greater than the number of outcomes in the complement. So our question that gets posed here, where we're going to use this formula, it says a restaurant gives a free fortune cookie to every guest. The restaurant claims there are 500 different messages hidden inside the fortune cookie. What is the probability that a group of 5 people receive 2 fortune cookies with the same message? Okay, so the first question they ask here is count the number of ways to get 5 messages. All right. Initially, I couldn't figure it out quite yet, but what I decided was let's look at something smaller. Let's say you had 3 messages in the fortune cookie and you wanted to figure out, all right, let's say there were 3 messages and you were given 2 fortune cookies, okay? So let's say you had message A, message B, and message C. So you could have had so if I made a list of it, you could say you could have had a message A, message B for 2 fortune cookies, a message A and a message C, and you could have also had 2 message A's. You could have also had a message BA, because it's like a permutation. So the first one was B, the second one was A. You could have a message BC, and you could also add a message BB. You also say you could add a message CA, you could add a message CB, and also a message CC. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. You could have 9 messages. Well, how does that correlate with these numbers 3 and 2? Well, it's 3 to the second power. 3 to the second power gives us 9. So the base number 3 in this case was the number of messages that were given, and the exponent is the number of times that you were given that message. So the number of ways that we could get 5 messages, well, there were 500 messages that were given for the fortune cookies, and There were five received, so it'd be 500 to the fifth power. 500 times 500 times 500 times 500 times 500. All right, really big number. It's in like the trillions. So what we wanted to know is we needed to find ways to get five different messages. So the first message, you could have one of 500. Times it by the second message. Now, if they're different, it's subtracted it, so now it's going to be 499 subtracted by 498 subtracted by 497 subtracted by, so now we got 496. So that's how we can say we can get five different messages. All right, that's another really big number. So it says probability of at least two messages are the same is we're going to look at the complement, which is 1 minus the probability of none are the same. And that's where we'll use this here to give us an idea. And to set this up, it's going to be 1 minus, all right, the um, the number of favorable outcomes where there none are the same. It's going to be 500 times it by 499 times it by 498 times it by 497 times it by 496 divided by the number of possible outcomes, which is 500 to the fifth power, which is 500 times 500 times 500 times 500 times 500. So if we look at that, so what I would do is put in my calculator. So in parentheses, 500 times by 499 times by 498 times by 497 times it by 496. Close the parenthesis. Then I'm going to divide it by, and I'll put another set of parentheses. It's going to be 500 times 500 times 500 times 500 times 500, and I'll hit enter, and I get 1 minus 0.98. And if I were to subtract that, I would get 1 minus 0.98, and that is by about 0.02. So to have at least two messages that are same, you have a 0.02 or about a 2% chance of that coming true. All right, so here what we have, it says in the diagram below, it illustrates the possible outcomes when two six-sided dice are rolled. So you can either have like a 1-1, 1-2. So they have all of the possible outcomes here. So if you count them, there are 36 possible outcomes. So the questions that they pose here is, what is the probability that the sum is 7? So, we could have like a 3 and a 4. We could have a 6 and a 1. Stuff like that. Let's see here. So if we count it out, we got 1, 2, 3, 4, 5. We got 6. So we have 6 out of a possible 36 outcomes, and reduce that, that's 1 out of 6. So the question now is, what is the probability that the sum is not 7? So you can use a complement of 1 minus the probability of them being a sum is 7. We could say it's 1 minus 1 out of 6, and say that that is going to be, what we could say, like 6 out of 6 minus 1 out of 6, which then gets us 5 out of 6. And then finally here it says sums that are greater than 9. So everything that's greater than 9, it's here. We got 1, 2, 3. Um, that's 8, 9. That's 9. So has to be greater than 9. So it looks like there are 6. There are 6 out of 36, and again, that is 1 out of 6. Okay, and that is being able to find the probabilities of disjoint and overlapping events. Hope this helps. Until next time.